All right, so what did you come up with your marshmallow shape? A lot of people, even though I'm very specific about saying don't do it two-dimensional, come up with something like this. So I'm using balloons right now for the manipulative. They make a plus. The problem with the plus is it's only 2 dimensions, right? You've got nothing up here and you've got nothing down here. You just have this one plane. So this is actually not as far apart as you can get 3 things because we're not taking advantage of all the planes around the central atom. If I shake this, you're gonna see what shape you get. This is the shape that 4 things are gonna take on. Notice that 3 of them are hanging lower, 1 of them is above. This is called a tetrahedral. This is as far apart as you can get 4 things. So with the marshmallows, it's a little bit easier to see. So we don't want a plus, we want 1 above and 3 kind of pointing below. So this is the shape of a tetrahedral. Notice that if I rotate it, it's basically the same shape. Now, obviously, I'm a person and making mistakes with angles, but for the most part, it's the same shape no matter which way I turn it because all of these angles are the same. This angle is 109.5 degrees. So when you have 4 bonding and 0 non-bonding orbitals, you get the shape that's called a tetrahedral. And the shape, when we draw it on paper, we don't want to make it look like a plus. Lewis structures can be pluses. 3-dimensional shapes need to imply an angle other than 90 degrees, okay? This angle and each one of the angles is 109.5 degrees. So with 4 electron domains, all of them bonding, none of them non-bonding, you get a molecular geometry and an electron geometry that are tetrahedral. So this is both electron geometry and molecular geometry. That's the shape that you get. So carbon, silicon, germanium, anytime you have a molecule with those 3 atoms in the center, you have 4 bonding, 0 non-bonding orbitals, you get this tetrahedral shape. And the angle is 109.5 degrees. All right? Okay, we're gonna move on to group 5. Okay, so group 5 would be something from obviously column 5, so I'm gonna do nitrogen. I'm gonna do NH3. Okay, now think about the Lewis structure that you learned. The Lewis structure for NH3 looked like that. Okay, we had 1 non-bonding pair and 3 bonds. Okay, but hybridization takes place. So let's see if anything is different. So nitrogen normally looks like that. There's my non-bonding pair. There's my 3 bonding orbitals, but hybridization still takes place. So the S and the 3 P's, so I still wind up with sp3 hybridization because all 3 P's are involved. But now with 5 electrons, I have 1 non-bonding orbital. Okay, so I have a total of 4 orbitals. So with 4 orbitals, my electron geometry is still tetrahedral. But now I have a different situation. I have 3 bonding and 1 non-bonding. So my molecular geometry is going to be a little bit different. So let's see, let's go back to the marshmallows and see. So here was CH4. How do I convert this into this? Think for a minute. What do I need to take away? Do I need to take away a marshmallow and a stick? Hopefully you're saying, no, I don't have to lose it all. I only have to lose the marshmallow, right? The stick still needs to be there. So I still have my tetrahedral geometry, but now there's no atom up here. So now the molecular shape is just based on these 3 marshmallows and the center atom. So this is no longer called tetrahedral because there's nothing up here. This is now called trigonal pyramidal or triangular pyramidal. Trigonal is usually the term that you're going to hear. Okay, so the molecular geometry, put down my marshmallow for a minute, is called trigonal pyramidal. Sometimes you'll hear it triangular, but usually trigonal. Okay, and how do I get that? Because one of these 4 tetrahedral orbitals is a non-bonding orbital. There's no atom attached to this. So when I draw it, nitrogen loses anything up here. Now that pair of electrons is there, but it's not part of the molecular shape. Okay, so the H's are all kind of at the base of a 3-sided pyramid. Triangular pyramidal is how you get that. Okay, this angle is almost 109.5. It's a little bit less, and here's why. So it's a little bit less than 109.5 because this lone pair of electrons takes up more space than a bonding pair of electrons. So non-bonding orbitals actually are bigger than bonding orbitals because in a bonding orbital, the electrons are held between 2 atoms, so their location is more focused. With a non-bonding orbital, the electrons can spread out more because there's nothing holding them in a certain location. So this orbital is actually a little bit wider than these 3, so it winds up pushing. You just get a little bit of pushing down so that the angle here between the 2 atoms is a little bit smaller. Not a lot. It's actually, for those of you who want to know, it's actually 107 degrees. You don't ever have to worry about knowing that number, but that's what it is. It's 107 degrees when we have 1 non-bonding orbital. All right, so let's review again because we're going to jump to group 3 in a minute here. So we've got total of 4 orbitals. Total of 4 orbitals. Same electron geometry, tetrahedral geometry, because I've got 4 electron domains. What makes these different is that here, one of these domains is non-bonding. They're all bonding here, I get tetrahedral. Only 3 of them are bonding here, I get a molecular geometry that's different. I get a molecular geometry that's trigonal pyramidal. Okay? How are we doing? Okay, so group 5, 3 bonding, 1 non-bonding. We're going to jump to group 3. Okay, so group 3, the head of group 3 is boron. Boron is a metalloid, so boron will form covalent bonds. It's the only element that's going to form covalent bonds, but we're going to use it. So if I want to form boron hydride, trihydride, okay? Think about what boron is. Boron has 3 valence electrons. It's group 3, right? So the S is filled and 1 of the P's. Well, guess what? Just like the other 2 groups, hybridization takes place. So 1 of these electrons is going to get promoted to 1 of the S's, from the S to 1 of the P's, but notice the 3rd P is completely empty. We always have to have 1 in the S, but in this case, there's not enough electrons for the P. So guess what happens? We only get 3 orbitals hybridizing. So we have the S and 2 of the p's hybridize. So guess what kind of hybridization this is called? sp2 hybridization. When you have sp2 hybridization, you have a whole different kind of electron geometry. We only have a total of 3 domains, right? There's 3 bonding domains, and there's 0 non-bonding. Okay, so compared to the other groups, 4 and 0, 3 bonding, but 1 non-bonding, still a total of 4. Over here, we only have a total of 3. So something different is gonna happen. So boron hybridizes to make sp2 hybridization, but let's go to the marshmallows and figure out what's gonna happen. Okay, so this was NH3. Okay, I lost an atom, but I didn't lose a stick because of that pair of electrons. Boron doesn't have that pair of electrons. So guess what I have to do? I have to lose the stick as well. Well, whoops. Once I take the stick away, is there any reason for this 109-degree angle to stay there? No, look at all this empty space up here. These 3 orbitals are going to spread out. They're going to spread out and take up space. And guess what angle we wind up with? We wind up with an angle that's 120 degrees. So this actually does wind up being planar, because that's as far apart as you can get 3 things around a central point, 120 degrees. So what we have is, again, because there's no non-bonding orbitals, the molecular geometry is going to be the same as the electron geometry. They are both going to be what we call trigonal planar, a 3-sided plane. That's why I like the marshmallows, because I can manipulate them to do what I need them to do very easily. Okay, a 3-sided plane, trigonal planar. So planar when I have 0 non-bonding, pyramidal when I have 1 non-bonding, and 3 bondings in both cases. Okay, so I'm going to draw this at a 120-degree angle. So that's group 3. All right, so with the marshmallows, I compared it on the board, but let's compare with the marshmallows. So here's group 3, 3 bonding orbitals, 0 non-bonding. Soon as this stick comes in, what happens? This pair of electrons forces these 3 down. I take it away, they expand. I put it back, they decrease. So there's the electron repulsion. Without that 4th orbital, I get 120 degrees. Put that 4th orbital in, and instantly these guys get repelled to 109.5-ish, 107 technically. Okay?